Hi, I'm Celine the Tulip, and today I'm going to talk to you about using a linked list structure to implement a stack. Okay, so let's get started. Now let's think about our stack abstract data type, and these are the methods that we need to implement if we want to create a stack. We need to be able to push elements onto the stack. We need to be able to pop elements off the stack. We need to be able to peek and see what element is at the top of the stack. We need to find out how many elements are in the stack using the size method, and also we want to be able to check and make sure, see if the stack is empty. So how are we going to implement these items using a linked list, using our linear node data container? So here's a picture of a linked stack of turtle objects. So what we are going to need to do is keep track of a reference to one of our linear nodes, and this is going to be our top variable. So this is going to always point at the element that's at the top of the stack. So here top points to our linear node, and the linear node contains an element reference that points to the turtle object. So this is the turtle at the top of the stack. Now this linear node also has a self-reference in here to another linear node. So this is the second node down the stack, and it contains the turtle that's second down the stack. And again, another link to another linear node. Now this is the linear node at the bottom of the stack, so the reference is null because it's not pointing to any more linear nodes, but there still is this turtle object down at the bottom. And in addition to our top reference, which gets us access to the top of the stack, because this is actually a reference, in other words, a pointer to a place in memory, it's not a number. So in our array implementation, top was both an index into the array and a counter for how many elements on our stack. In this case, top doesn't serve that purpose. It's only a pointer, and so we need to separately keep track of the number of elements in our stack, and that's what the count variable here is for. So let's imagine that we want to push another element onto the stack, another turtle. How do we do this? Here is the process. The first thing that we're going to do is we're going to create a new linear node, and we're going to pass in the element that needs to be pushed onto the stack. So here's our node, and we pass in this fourth turtle object and link it into the element of our linear node. The next thing we need to do is we're going to assign the nodes next to be the same as whatever top is. So we're basically copying this memory location here over into this slot. So now both of these are pointing at this element in the stack. The next thing we need to do is now change top so that instead of pointing at this one, it's now pointing at this linear node. And of course, the last thing we have to do is increment our counter so that it shows that we have 4 turtles in our stack. So that's the basic push operation. What isn't shown here and what you'll need to make sure you remember is when you first create this linear node, the new one, you're going to have to somehow temporarily store a reference to it so you can get access to it and do things. And then afterwards, once you've got this set up and top is pointing to this linear node, you'll no longer need that reference. Okay. The next thing that we want to talk about is the pop method. So when we're popping, we're removing the item off the top of the stack. So what does this look like? So here we're going to assume we've got these 4 turtle objects on our stack. The first thing we're going to do is we're going to use our top reference to get to this first node. We're going to get the element from it, and we're going to store a pointer to this turtle object. So we're going to probably call this temp, and we're just going to store this, a reference here. So really what we're doing is we're copying the memory address that's here over into temp. The next thing we're going to do is we're going to get next from the first node right here, and we're going to copy it to top. So because we want to remove this element, we need top to point over at this one. So we're copying this address here out of this node, and we're going to put that into top. Okay. The next thing we need to do is decrement count so that we no longer say that we have 4 elements. And then we need to return the stored element. And so we'll return the stored element. And what's going to happen after this is that this linear node that's sitting here right now, it still points to this linear node. It's still got a pointer to the turtle object, but there's nothing pointing to this linear node. And so Java's automatic garbage collection will eventually come along and get rid of this. Okay. Peek is the easiest one, of course. So it looks like this. We're going to use the top reference to get to our first node. We're going to get the element from it and store it in a temp variable, just like we did with pop. Okay, so now we have this temp variable that's pointing to this turtle object so that it can be peeked at and people can inspect it and look at it. And then we're going to return that element, and that's it. Nothing else changes because, of course, peek doesn't really change your stack. And I haven't shown what is size and, size and is empty look like, but size will clearly just return count, and is empty will return Boolean true or false, depending on whether count is 0 or not. So they don't really need diagrams. Okay, so complexity analysis, if you were to compare implementing a stack with an array versus a linked list, they really are pretty much the same. The only difference really is that with the array, you eventually have to expand the array if your stack gets really large, or you might have to expand the array. But even with that, cost gets amortized over all of those other pushes onto the stack. So it's still really order of one. But there's just, in some sense, you don't have to worry about that as the programmer. So really, both of these implementations are very, very efficient implementations of a stack. Okay, that's all. Thanks for watching.